What's up, everybody, and welcome back to 3 Inquisitive Kids. You're almost there. This is the last lesson of Chapter 4. Thank you for sticking through it with me. So, in this past chapter, we learned a lot about linear functions, proportional linear functions, their graphs, their relational expressions, all of that good stuff. And in this lesson, we're going to be comparing linear functions with more than one graph. So when I say that, I mean think about a coordinate plane with multiple graphs of linear functions plotted on there. Again, this is the final parts to applying linear functions, which is the last video we're going to have for Chapter 4. So yeah, let's get started. The learning goals for today are to master the application of two linear graphs of linear functions and able to use functional graphs to solve word problems. Introduction. Observe and think. Looking at the figure to the left, what differences do you observe between the three functional graphs? Here we have a x-axis and a y-axis, and it's a unit of centimeters. So there's a toy car and it rolls down. This is the slope it goes down. And then it goes like that. Then it's the highest slope. It goes down immediately like that. So what are the differences you may observe from looking at that animation? Well, something I observe is that the speeds of the different times that this car went down changed. For example, what I mean is when the slope was only to the 40 rack, it came down at a pretty slow speed. But as it went higher, it went faster and faster. It accelerated. The speed accelerated. So that's one of the things that you might observe when looking at these animations. Application of two linear functions. Introduction. L1 reflects the relationship between the sales revenue and sales volume of a company's products. Fill in the blank according to the graph. When the sales volume is 2 tons, the sales revenue is blank dollars. Well, here you don't really have to know what it means, right? You don't really have to know the exact definition of sales revenue and sales volume. Of course, it's always a good thing if you do know, but to solve this problem, you don't exactly need to. All you have to do is look at the graph. So, for example, it says when the sales volume is 2 tons. Well, the sales volume, so that's in tons, that would be the x-axis. So we can trace our finger to where that is 2, and then we find its corresponding point, which has a y-coordinate of 2,000. The sales revenue would be $2,000. L1 reflects the relationship between the sales revenue and sales volume of a company's products. The relational expression of function L1 would be blank. Again, you can use the information and the knowledge that we've learned before in the previous lessons about relational expressions to solve this problem. And that would be y is equal to 1000x. So again, to review how we got this answer, we first have y is equal to kx plus b. So b here is the y-intercept, which is 0, so we don't have to include that. And k would be, remember, change in y divided by change in x, which would be 1000, because for every increase of x, that is 1, y increases by 1000. So right there. Okay. L2, now we have a different function. Reflects the relationship between purchase cost and sales volume. The relational expression of function L2 would be blank. So using the same steps as the last problem, we should get y is equal to 500x plus 2000. Now we have a y-intercept because here in the graph there is a y-intercept, which is plus positive 2000. When the sales cost is $4,500, the sales volume is equal to blank tons. So to solve this problem, we need to first look at the sales cost, which is the y-axis, and that is $4,500, which would be this point right here. Now we trace that to its corresponding point on the graph, which has a x-coordinate of 5. So the answer for this problem would be 5 tons. When the sales volume is 6 tons, the sales revenue is blank dollars, and the sales cost is blank dollars, and the sales profit is blank dollars. All right, so sales volume, when that's 6 tons, 6 right there, that would be $6,000. That means the sale cost, so this point right here, is $5,000. It's just on a different function. And then the sales profit would be $1,000. And now this is where you do need to know some economics, because profit is the revenue or income minus the cost. So all you have to do is subtract, and that's why this part right here is the profit. And now although this is pretty basic, it is something that people in real life do. When they work, you do have to look at graphs and stuff. So this is all very important skills that you need to have when you move on in society. When the sales volume is blank, sales revenue equals the cost of sales. Sales revenue and the cost of sales are both $4,000. So it's also asking, more mathematically, what is the value of sales volume that causes both the sales revenue and the sales cost to be the same value, where they're both $4,000? Well, you could just look at this intersection point right here. This point is where both the sales revenue and the sales cost is the same and is exactly at $4,000. So the x-coordinate of that point would be 4 tons. So there's a couple of more questions here. When the sales volume is blank, the company makes a profit. When the sales volume is blank, the company loses money instead. So first, we have to know the mathematical terms of how to describe making profit and losing money. So remember how I told you that profit is equal to revenue minus cost, or income minus cost. That is equal to profit. So when we have a profit, that's when the profit is, of course, positive, where the revenue is greater than the cost. So that would be this point right here, greater than 4 tons, because if you look at the graphs of these two functions, we want the revenue to be greater than the cost. It is past point P, so all of these values right here, where we will make a profit. If it's anything lower than that, if the sales volume is anything lower than 4 tons, we will start losing money, which is this section right here. A negative profit would just mean losing money because you're not gaining anything back. So what else do you observe? Think, what are the real meanings of K and B in L1 and L2? What do K and B really represent? Well, K indicates the amount of income or increased cost per ton of product sold, and B indicates the starting value of the changing value, which is the y-intercept where it starts off. For example, K1 represents that the sales of each ton of products, not projects, products can earn $1,000. And K2 indicates that the cost of sales per ton is $500. B1 represents that the cost of sales will gradually increase from $2,000. So now let's do another problem. Example 1. Ship A is a pirate ship that is sailing into Ship B's territory. Once Ship A is spotted, Ship B is sent to chase it. So we have ship A right here and ship B right here. This is land, and this pale blue area is quote-unquote ship B's territory. Below, L1 and L2 each represent the distance of the two ships relative to the coast, this green area right here, and the relationship between S and T. S, which is the nautical mile, which is a unit we use when measuring traveling in the sea. And T is in minutes, which is, of course, minutes, how far they're into the chase. So that is what S and T, those are their units. Okay, so the first question is, which graph represents the distance of ship B relative to the coast? What here can tell you that, if this is relative to the coast? Well, the main difference that you might see from these two functions is that one of them has a y-intercept of 5 and the other has a y-intercept of 0. Remember, the y-intercept, or b, you can think of as the starting point of the changing value. So when they started, the pirate ship was further away from the shore than ship B, which is the ship sent to chase it. Therefore, L1 would be ship B. Okay, now that we kind of understand and we've labeled both of these graphs, I'm going to ask you which ship A or B has the faster speed. Well, now more mathematically, it's asking you which function is increasing at a faster speed, at a faster velocity. Well, all you have to find is changing y over change in x. And also, if you're just looking at the scenario, ship B is chasing ship A. So if you're chasing someone, your speed, and they already have a head start, your speed has to be faster than the other person in order for you to catch up. So when t increases from 0 to 10, the y-coordinate of L2 increased by 2, while the y-coordinate of L1 increased by 5. Therefore, within 10 minutes, A traveled 2 nautical miles and B traveled 5 nautical miles, so B's speed is faster. So can ship B catch up to A within 15 minutes? As you might see right here, these two graphs aren't completely touching yet. That's because they haven't fully caught up to each other yet. So, but within 15 minutes, will they be able to do that? Well, all we have to do is just extend these two functions until they do. When t is equal to 15, the corresponding point on L1 is below the corresponding point on L2. This means that when they had chased for 15 minutes, B had not caught up to A yet. But if they continue at the same speeds, will B catch up to A? Well, this is where we can extend where they possibly will be in the future, which is when they intersect at point P. So yes, if they do continue at the same speeds, if they just have a bit more time, then B will eventually catch up to A. Yes, that is true. When A flees B's territory 12 nautical miles away from the coast, B will stop chasing it. At this speed, can B catch A before A escapes? So now we have another circumstance where we have to think about, will A flee away just in time? Will it be spared from B? Well, let's think. By the time they catch up to each other, P, is it before 12 nautical miles? Are they 12 nautical miles away from the coast yet? No. That is because the y-coordinate of point P is less than 12. This shows that before A flees, boat B is going to be able to catch up to A. Among the two linear functions, y is equal to k1x plus b1 and y is equal to k2x plus b2, and they're corresponding to L1 and L2, what meanings do k1 and k2 have? And what are the speeds of A and B? K1 represents the speed of B and K2 represents the speed of A. And their corresponding speeds are 0.2 nautical miles per minute and 0.5 nautical miles per minute. Practice. Below L1 and L2 are the graphs of the ST function, so S in meters and T in minutes, of the tortoise and the hare. So I'm sure that most of you guys have heard the children's story of a tortoise and the hare racing. And in the end, the tortoise reaches the finish line before the hare does because the hare stopped down to take a break because they were so arrogant of themselves. But anyways, this is the graphs that represent the tortoise and the hare. Although in here, for more simplicity, the hare does not stop and take a rest. So first, the question is, what meter race is this? Well, all you have to do is find the y-coordinate at which both of these functions stop, which would be 100. This is the 100-meter race. And which one would be the graph of the hare? Well, we know the hare is faster than the turtle. So that means that the hare will have to be the one that reaches the finish line first. Therefore, L2 is the graph of the hare. When the hare reaches the finish line, the tortoise is still blank meters away from the finish line. So now we're looking at when, which indicates us to look at the x-coordinate t, or minutes. So this is when they have run for 6 minutes is when the hare have reached the finish line at this point. So here, the hare has already reached the finish line, but the tortoise is still struggling, but persisting at 60 meters through the race. So the tortoise is still 40 meters away from the finish line. Okay. If the tortoise and the hare reach the finish line at the same time, so if they were to do that, how much of a head start should the tortoise have? Well, this is harder because then we would have to think about this as shifting the L1 left so that this point right here lands on the same point as the ending point of the hare. So we can think of this as shifting it back so that L1 has a y-intercept of 40. So the tortoise and the hare, if they were to finish at the same time, the tortoise must first have a 40-meter head start. If the tortoise were to reach the finish line first before the hare, how much does it have to run at least? So how much more minutes does it have to run earlier than the rabbit? It would have to run 4 minutes earlier than the rabbit. Example 2. Given that linear functions y is equal to 3/2 of x plus a and y is equal to negative 1/2 of x plus b, both intersect at point A, which is negative 4, 0, and the y-axis intersects at B and C, find the area of triangle ABC. Well, first we need to find the points, the coordinate values of all 3 of these points. So since both of these functions intersect at point A, we know that 3/2 times negative 4 plus a is equal to 0, and negative 1/2 times negative 4 plus b is equal to 0. Therefore, we know that a is equal to 6 and b is equal to negative 2. So we know the two functions are y is equal to 3/2 of x plus 6 and y is equal to negative 1/2 of x minus 2. Since this function and the y-axis intersects at b, then we know b has the coordinates 0, 6. And since y is equal to negative 1/2 x minus 2 and the y-axis both intersect at c, therefore y is equal to negative 2 and the coordinates of point C are 0, negative 2. As shown in the figure, the area of triangle ABC would come out to be 16. So method summary. To solve this kind of problem, you first need to obtain the coordinates of the vertices, these the points on the triangle, which is A, B, and C. And in order to do that, you must first obtain the relational expressions of both of these functions. Class summary. Today we learned about the graphs of multiple linear functions. We looked at real-life problems and solution selection problems. Today we mastered the application of two graphs of linear functions, and we were able to use functional graphs to solve word problems. Thank you so much for watching Three Inquisitive Kids, and we'll see you next time.